Second talk of the session, we have Sarah Brauner from University of Minnesota, and she's going to be talking about Eulerian representations for real reflection groups. Sarah, the floor is yours.
Thank you. And thank you so much for the opportunity to talk. I'm very honored to be speaking today. So what I'm going to talk about today is work that's going to appear in the Journal of the London Mathematical Society. And so the big idea of this talk is that I want to take some nice type A story that brings together topology, combinatorics, and representation theory. And I want to generalize that to the reflection group context. So in the type A story, there's some sort of important objects running around. So on the topological side, we have configuration spaces and their cohomology. And on the combinatorial side, we have the Eulerian idempotence of the symmetric group. So my goal today is to tell you in more detail what happens here, and then to tell you about my contribution, which is to generalize this in two different ways. So the first way is when W is what's called of coincidental type. So this is a type of Coxeter group. If you were at FPSAC in 2019, Vic's talk, which was delivered by Nathan Williams, was all about these coincidental groups, which I'll say more about what they are later. But in this coincidental context, the type A story generalizes in exactly the way that we want it to. And in particular, the combinatorics work really well. And then more generally, when W is any finite Coxeter group, there's a similar, slightly more technical statement that we can make that looks very similar to this type A story. Okay, so my plan today is to first tell you what happens in type A specifically, and then I'm going to tell you about the objects we need for our generalization, and then I'll tell you about the two generalizations, starting with the coincidental case and then moving on to the more general Coxeter group case. Okay, and so this really, the story really begins with the descent set of a permutation. So here I'm thinking about sigma, my permutation in one-line notation, and my descent set is keeping track of the indices where sigma I is bigger than sigma I plus 1. And then the descent number will just count the size of that set. So for example, here, if this is my permutation, sigma, we can see, okay, 1 is smaller than 5, but then 5 is bigger than 3. So that tells me I have a descent at position 2. And then similarly, 4 is bigger than 2. So I have a descent at position 4. And if I count this set, it's size 2. So that's my descent number. If you're comfortable with the language of Coxeter theory, there's actually, this is a very general idea, this descent. So I can define it for any element in a Coxeter group where now it's defined via Coxeter length, and my descent set is comprised of simple generators. And the descent number is defined in the same way. Okay, so one interesting thing that has come out of this descent statistic is a result of Solomon, who proved that for any Coxeter group, I can define a subalgebra of the group algebra of W that's spanned by sums of elements with the same descent set. So I'm going to call this subalgebra Solomon's descent algebra. And the sort of surprising thing here is that this definition is that it's closed under multiplication. Okay, so for example, in S3, what does this look like? Well, here are my 4 possible descent sets. And what I do is I just take all of the permutations that have that descent set. So for example, which permutations have a descent set of 1? These 2 here. Okay, so the combinatorial objects that I'm going to be interested in type A were introduced by Garcia and Rettenauer, and they're called the type A Eulerian idempotents. So they're a family of orthogonal idempotents. I'm going to write them like this. They live in the descent algebra of the symmetric group, and they're going to run from 0 to n minus 1. So I'm going to have n of them. And they're defined via this nice generating function here. So this right-hand side is a binomial coefficient. And if I were, for example, in S3 to expand this formula and take the right coefficients, these are the 3 idempotents that I would get. And you can check that these actually are in the descent algebra. Okay, so I'm going to be interested in representation theory related to these idempotents. So to review, irreducible representations of the symmetric group are indexed by partitions of n. So when I'm talking about an irreducible, I'm just going to write the partition down. And in particular, the representations that I'm interested in are going to be generated by each Eulerian idempotent in the following way. So I take my idempotent and I think about the ideal that it generates in the group algebra. And this is going to give me a symmetric group representation. I'll get 1 for every idempotent. and I'll call it the kth Eulerian representation. So a nice special case for experts is when K is 0, this representation is isomorphic to the multilinear component of the free Lie algebra. Okay, so for S3, what do these things look like? Well, we saw that this idempotent here, for example, is an unsigned sum of every permutation in S3. So if I act on it by multiplication, it's going to rearrange the terms in my sum, but it's not going to change them. So it'll act trivially. Another way of saying that is that this representation is the trivial representation of S3. Okay, and the other ones are a little harder to see, so I'm just going to tell you, when K is 1, we get this decomposition, and then when K is 0, so the Lie case, we get that representation. And you might notice that altogether, this gives me the regular representation of S3. And that's going to be true in general. I'm going to get some sort of decomposition of the regular representation of Sn in general. Okay, so these representations were arising as from idempotents in the descent algebra, but it turns out they actually come up in another context also, which is the context of configuration spaces. So the configuration space that we're going to care about is called the nth ordered configuration space of R to the D. I'm going to write it like this. It's defined as the set of tuples x1 through xn. So each of these xi's lives in R to the D. And I'm just going to require that they're distinct. So for example, if D is 1, let's say n is 3, this set is now just the set of points in R3 where each coordinate is distinct. So I could draw a picture of this by saying, okay, well, these planes here are the planes where 2 of my coordinates are the same. And so my space is just going to be the complement of these planes. Okay, and if this picture might be very familiar to people, or if I project along this line where they intersect, maybe this is a more familiar picture of the rank 2 braid arrangement. And then this will come up later. Okay, so this is a very classical topological space. And so a natural question is, what is its cohomology? And this was computed by Arnold and Fred Cohen. Here's the presentation. And I don't want to dwell too much on the details of this presentation. I just want to note a couple of things. So first of all, this theorem is for D greater than or equal to 2, but if you stare long enough at these relations, you'll notice that the only place that D is coming up is in these -1 to the D plus 1 coefficients. So that tells me that the presentation only depends on the parity of D. So I'll get an odd presentation and an even presentation. So for example, D equals 3 and 5 will look the same. And then again, if you look at these relations and you notice that this generator lives in cohomological degree D-1, that's going to tell me that the cohomology is concentrated in degrees that are multiples of D-1 from 0 up to n-1 times D-1. So the point is I have n pieces here, similar to the Eulerian representations. Okay, so we understand this presentation pretty well. A maybe more nuanced question is, what does this cohomology ring look like as a symmetric group representation? So we're getting a symmetric group representation here from the action on this ring of the generator. So sigma will permute the generator's indices. Okay, that's going to induce a representation. You can ask, what does that look like? And it turns out in the case that D is odd, if I ignore the grading and just look at the total cohomology ring, what I'll get is the regular representation of Sn. So this should start to tell you that this D odd case is the one that's relevant to us today, because the Eulerian representations also decompose the regular representation of Sn. Okay, and we can actually be very precise about what this connection is. So the key idea here is that there's an isomorphism of symmetric group representations where each Eulerian representation on the one hand is describing every graded piece of this configuration space cohomology on the other, in this case, that D is odd. And so the way that we knew this for a while was by character comparison. So Hanlon computed the characters of the Eulerian representations. Sundaram and Belker computed the characters of this cohomology ring, and you can check that they're the same. So later on, I'll give a proof that's a little bit, that doesn't depend on any character computations. Okay, so what is, in the case of S3, let's say D is 3, this part of the picture is known, we've seen it before. The new information here is telling you that each of these representations is describing a piece of a cohomology ring. And for experts, this ring has an NBC basis, and here's what it is broken down by degree. Okay, so in summary, on the topological side, we had this configuration space cohomology. On the combinatorial side, we had these Eulerian idempotents of the symmetric group, and then they were brought together by representation theory of the symmetric group. So the big question of this talk is this story actually a case of a more general phenomenon? Can we phrase this in terms of reflection groups? So the answer is yes. There's sort of two ways to do this. One is for these coincidental reflection groups, and then one is for any finite Coxeter group. And so what I want to do now is tell you about how each piece of this story can be sort of phrased in terms of reflection groups. Okay, and to do that, I'm going to use the fact that every reflection group, W, defines a hyperplane arrangement, okay? I'm going to write it like this. It lives in a real vector space V, okay? And the idea is the reflections in this group are exactly reflecting over the hyperplanes in my arrangement. The rank of this arrangement is just going to be the dimension of my vector space. So for example, in S3, my reflections are transpositions, and they're reflecting over these lines here. Okay, this is a two-dimensional vector space, and so the rank here is 2. Okay, so again, our goal is to phrase each of these 3 pieces of the story in terms of reflection groups. And I want to start with this configuration space cohomology. So I originally defined the configuration space, as this set of points in RDN that are distinct. But I want to rephrase that using hyperplane arrangements, and in particular, the hyperplane arrangement associated to the symmetric group, the braid arrangement. So these are hyperplanes where Hij is defined by setting xi equal to xj. And it turns out that I can equivalently define this configuration space using the braid arrangement as follows. So I take every hyperplane, I tensor it by a copy of R to the D. Okay, so I thicken it. I tensor this ambient vector space by R to the D. And then I remove these thickened hyperplanes, which are now just subspaces of this vector space. So the intuition here is when D was 1, we saw that this configuration space was exactly the complement of the braid arrangement. So this is some sort of generalization of that. I think it's a little bit less intuitive as a definition, but it has the advantage of being pretty easy to generalize to Coxeter groups. So I'm going to define this more general space, MDW, in the exact same way. I'll take my hyperplanes in my hyperplane arrangement associated to W. I tensor them by R to the D. I tensor this vector space by R to the D, and then I remove what's these subspaces. Okay. So for example, if I did this for BN, the hyperoctahedral group, what I would get is the set of points x1 through xn, where again, each of these xi's lives in R to the D, but now I require that xi is not equal to 0 and xi is not equal to plus or minus xj. So this is called the Z2 orbit configuration space in this case. Okay, so it turns out that a lot of the properties that we saw for this configuration space hold in this more general subspace complement. So W acts on it, and the cohomology carries a W representation. Again, the presentation of this cohomology ring has been computed, and it depends on the parity of D. In the case that D is even, this cohomology ring is isomorphic to the Orlick-Solomon algebra. So this is a very famous algebra in the world of hyperplane arrangements. And in the case that D is odd, it's isomorphic to what's called the associated graded Barchenko-Gelfand ring. So if you haven't seen this associated graded Barchenko-Gelfand ring, but you're familiar with the Orlick-Solomon algebra, what you should think is this looks a lot like the Orlick-Solomon algebra, except that it's commutative. Okay, so in both cases, the cohomology is going to be concentrated in degrees that are multiples of D-1 from 0 up to R. Okay, and again, if I ignore the grading and I just look at the total cohomology ring, it's the representation that it carries is the regular representation of W. Okay, so that's the topology. What about these Eulerian idempotents? Well, they've been sort of extensively studied and generalized since they were introduced by Garcia and Brauner. So Francois and Nantel Bergeron gave a type B analog or type B generalization And then soon after, Bergeron, Howlett, and Taylor generalized this to all finite Coxeter groups. Later, Franco Saliola generalized this to any central hyperplane arrangement. And then Aguirre and Mahajan recently have a book where they develop a lot more properties of these idempotents. So they're very well studied, but the definitions can be a little bit technical for a 25-minute talk. So what I want to do now is skip over these definitions. We'll see in a little bit that in the coincidental case, there's a nice way to define them. But for now, let's just take as definition that these elements E0 through ER, which live in the descent algebra of W, are my Eulerian idempotents of W, and they're going to generate a representation in the same way as the ideal in the group algebra of W. Okay, so we now have a good candidate for our topological space, a good candidate for our Eulerian idempotents. And so the question that remains is, are these two objects related at all? And if so, what can we say about them? Okay, and I'm going to start with the coincidental case. So every reflection group has an associated integer sequence. I'm going to write it like this, called the fundamental degrees of the group. So for experts, these are the polynomial degrees of the generators of the invariant ring. If that doesn't mean anything to you, just think some nice set of integers that I get along with my reflection group. So for example, for the symmetric group, the degrees are 2, 3, 4 up to n, all right? And a finite reflection group is called coincidental if its fundamental degrees form an arithmetic progression, meaning they increase by a fixed amount each time. So for example here, for Sn, these degrees are increasing by 1 each time, so that's coincidental. For Bn, the degrees are increasing by 2 each time, so again, that's coincidental. The other groups that we get are the dihedral group and maybe a little bit lesser known H3. Okay, so what makes these groups nice? The first thing is that they have nice subalgebras. So it was known in type A by Garcia and Brettenauer and type B by Francois and Untitled Bergeron that there's a subalgebra of the descent algebra that's spanned by sums of elements with the same descent number. So for example, in S3, this was my descent algebra. To get the subalgebra, I'm going to sum together the elements that have the same descent number. So these two are both size 1, so these elements become 1 element here. Okay, and then now I have a 3-dimensional algebra. And again, the surprising thing is that this is closed under multiplication. Okay, so it turns out that this is actually a very special property of the coincidental group. So the theorem is that there's a subalgebra of the descent algebra that's spanned by elements with the same descent number if and only if W is coincidental. And in fact, in that case, these idempotents are in this subalgebra and actually generate it. So that's why these subalgebras are sometimes called the Eulerian subalgebras. Okay, the next nice thing is that these coincidental groups have nice product formulas for these idempotents. So I sort of skipped over the definition of the general Eulerian idempotents, but it was known in types A and B that there are these nice special cases where we can define these idempotents via generating functions. And again, this turns out to be a case of a coincidental property. So when W is coincidental of rank R, turns out the Eulerian idempotents satisfy this generating function here. So I can define them via this generating function, where these DIs are the degrees, okay? And it also depends on the descent number and the rank R. Okay, and you can check that this generating function recovers these two generating functions here. Okay, and then perhaps most importantly, the coincidental groups, the topology behaves really nicely. So when W is a finite coincidental group of rank R, again, in this odd case, I have that every Eulerian representation is describing a unique graded piece of this cohomology ring of this subspace complement associated to W. which is exactly generalizing the type A result and sort of completing this picture that I showed you on the first slide. Okay, so how do we prove something like this? So these techniques are inspired by Barr. I'm going to define what I call a shuffle element in the descent algebra. And then you want to prove that this element acts semi-simply on the group algebra of W, and that these eigenspaces of this element actually are the Eulerian representation. So these Eulerian representations are arising in a third way as eigenspaces of some element in the descent algebra. So important tools that go into this are equivariant BHR, or Bidiger-Hanlon-Rockmore theory, that's due to Reiner, Saliola, and Belker. And then equivariant Gorowski-McPherson, which is due to Sundram and Belker. So part of the point here is that we want to avoid any character comparison or type-specific arguments using these techniques. Okay. And then I want to finish with what happens in this more general Coxeter group case. So in this context, I want to use the fact that this hyperplane arrangement is going to define a lattice. So I get the lattice. I'm going to write it like this. This lattice, it's the poset of intersection subspaces or flats that I get by intersecting my hyperplanes in all possible ways. Okay, and then I order them by reverse inclusion, and that gives me a poset, which turns out to be a lattice. W will act on this lattice. And so for any flat in my poset, I want to think about the W orbit of that flat. So for example, in S3, we've seen that this is the hyperplane arrangement associated to S3. To get the lattice of flats, I can intersect all of the hyperplanes. Okay, they intersect at the origin. So I get the zero subspace. I can take each line on its own. Okay, and I get these three subspaces, and then I can intersect nothing and I'll get the full vector space. Okay, in terms of the symmetric group action, it's going to send 0 to itself. So it's in its own orbit. And R2 is also in its own orbit. But then S3 is going to permute these lines. And so it turns out that, it turns out that these are all in the same orbit here. Okay. So the theorem is that for any finite Coxeter group W, there's a family of orthogonal idempotents. Okay, I'm going to write them like this. They live in the descent algebra of W, and they're going to be indexed now by flat orbits. Okay, they're going to generate representations in the same way, where I'm thinking about the representation generated by this idempotent in the group algebra. The ideal generated by this idempotent in the group algebra, such that in this odd case, okay, each graded piece of this cohomology ring of the subspace complement is being described by this sum of representations, okay, where I'm summing over representations indexed by flat orbits that have where the flat has a specific codimension. So K here goes with K there. Okay, and so the sort of technical part of this is how I'm actually defining these idempotents. But the point is that we have some way of describing each graded piece of this cohomology ring using representations generated by idempotents that live in the descent algebra of W. Okay, so in summary, our goal was to generalize this type A story here. And we saw that in the coincidental case, so when we had these groups with degrees forming an arithmetic progression, this worked really well, in particular, the combinatorics. So we had an Eulerian subalgebra, which is the algebra generated by sums of elements with the same descent number, if and only if W is coincidental. In the coincidental case, we had nice product formulas for those Eulerian idempotents. And then we had the representation isomorphism between each Eulerian representation and each graded piece of the cohomology of the subspace complement in the case that D is odd. More generally, for any finite Coxeter group, the graded pieces of this cohomology ring can still be described via representations generated from idempotents in the descent algebra. We just have to be a little bit careful about how we're defining these, or we're just summing now over representations with a fixed codimension. All right, thank you.
Okay, let's thank Sarah for a lovely talk. And the floor is open for questions. Well, I'll start off. Oh, by the way, Sam says great talk, Sarah, in the chat. So you're doing all of this for real reflection groups. Question then becomes, what if you look at complex reflection groups, especially the GMPNs should be a candidate because their degree sequences form an arithmetic progression.
Yeah, that I was hoping somebody would ask about that.
Yay, I'm happy to.
Yeah, so I would love to have some sort of way to talk about the complex reflection groups that are coincidental. So these are called the Shepherd groups in general, and they include that product. So it's a little bit, there's like two sort of tricky things. You kind of have a tricky thing on both sides. So on the topological side, we were really using the fact that we were in like an odd configuration or an odd subset complement. So we would have to come up with a way to think about that for complex. Yeah. Mm-hmm. But I think it's doable, but it might be like a little bit more complicated. And then on the combinatorial side, so for the Reith products, there's a notion of descent, and there are Eulerian idempotents. But more generally for Shepherd groups, we don't know, there's no length, and so it's a little bit hard to come up with a definition of descent, but it's something that I'm definitely interested in. And if anyone has ideas, I would love to hear them.
Good, good. So you're thinking about it. That's the important thing. Other questions?
It looks like there's a question in the chat.
Yeah, I put one in the chat.
Yes, there is. Thank you for it. I was looking at the bottom of the chat and it's a little further up. So Christophe Holweg asks, do you know how the EX idempotents relate to the Bergeron-Howlett tile or orthogonal idempotents in general?
Yeah, so so my understanding is that the BBHT idempotents are like kind of parametrized, and you pick these coefficients, and so these are a case of the BBHT idempotents. They are one specific family of BBHT idempotents. They're just, the way that I actually define them is using Lagrange interpolation. So I have some element in the descent algebra that acts semi-simply, and you can take the projectors onto each eigenspace. So they are the same, but it's just one particular instance that isn't using, I think, in like the language of Aguiar and Mahajan and Franco Saliola, the uniform section.
So if I may, so that means those orbits you're talking about of the action of W on LAW are what we call Coxeter classes. So they're also orbits of they are conjugacy class of the action of W on the subsets of the generators. Those
exactly.
Okay, thank you.
Okay, time for one last short question because we're almost at the hour. Yen Zhang says, really cool results about the existence of Eulerian descent algebras and coincidental reflection groups. Do you have a sense whether the existence of any other subalgebras of Solomon's descent algebra induced by other permutation statistics can be generalized to coincidental groups as well?
That's a good question. I guess I'm interested what subalgebras you're talking about. That might help me answer. I haven't thought a ton about other subalgebras, but it's possible.